It's really an honor for me to be here, and I really appreciate this opportunity to be here and talk about my research on fluid mechanics and turbulence, and also, in particular, my SAPERE project on physics-constrained learning for turbulent flows. But before I start, let me introduce myself. My name is Mahdi Abkar. I'm originally from Iran. I did my bachelor and master in Tehran Polytechnic, and then I moved to Switzerland in the beautiful city of Lausanne. I did my PhD there in 2014. And after that, I moved to the States, to Stanford University as a postdoc. I was there for 2 years. And then in 2017, I started my position at Aarhus University. And currently, I'm an associate professor and the head of section for fluids and energy. I'm also leading a research group in fluid mechanics and turbulence. As you can see here, my main research interest is around computational fluid dynamics, wind farm modeling and control, very relevant to Denmark, of course, boundary layer turbulence, and relevant to this talk, data-driven modeling and machine learning. So today I'm going to talk about turbulence. Turbulence basically is one of the most interesting topics, at least in my opinion, and perhaps one of the hardest problems in computational science. It's considered as one of the oldest unsolved problem, is better to say that, in classical physics. So it's very difficult to define that, at least in a short but complete way, but it can be defined, at least in a broad sense, as a chaotic fluid motions across a wide range of scales. It might seem a bit complicated, but I try to explain that by looking at this beautiful sketch by Leonardo da Vinci. This is perhaps one of the first recorded attempts to study turbulence in a scientific manner. So, and I should say that this is before the Newton's law actually kind of, derived. So here we can see the main property of turbulence. As you can see here, it's highly unsteady. It's three-dimensional. It's somehow random-like. It's not completely random because we can see some sort of coherent structures here. So, and it can be visualized by these, kind of irregular swirling motions that we see over different sizes. So these are actually this vertical structure that we can see in this sketch. We call them in fluid mechanics turbulent eddies. I use this term turbulent eddies a lot in this talk. And also, it increases mixing. So this is one of the main properties of turbulence. That's why, so we can kind of, use sugar in our coffee, and then by stirring that, that's actually the work done by turbulence. So what I want to emphasize here is, unlike some other disciplines, perhaps, for example, how the brain works. So I should be careful about that, but at least perhaps currently we don't have the exact governing equation for that, but in fluid mechanics and turbulence, we know the equation. So we know the governing equation here, and which tells us about the dynamic of each of these small vertical structures and also the large ones. But the challenge is there is no solution. At least there is no analytical or simple solution to that. So I will get back to that how we are going to solve this problem. But the next question is why we need to study turbulence. So as I think it's trivial that turbulent flows basically are everywhere in nature and engineering. I provided a few examples here, like, for example, the ocean-breaking waves, Jupiter's turbulent atmosphere, Kármán vortex street behind this mountain, and many other examples, so you can name it. But also in the engineering disciplines, turbulent flows are the key in many sectors, like energy, transport, health. And as an engineer, we are always interested to optimize the design and operation of these systems. So, for example, we want to have more productive, less expensive wind farms. We are interested to have more efficient aircraft, or better or more accurate, more reliable weather forecast model. So these are actually, I can go one step further. If we want to go toward the full green transition of our society, so fluid mechanics and turbulence would be part of that. But today, computer models, or what we call numerical simulation, basically is a major and the most cost-effective tool for these purposes. So basically, we are interested to use computer models before spending lots of money for building and testing prototypes. So I think the use of the intention behind using more and more computer models is clear here. But what is the challenge? So the main issue here is, even if we consider the exponential growth of computing power, it would be impossible to solve many of these problems in a direct and exact way. So here I just show a plot to show you what is the current status of the numerical simulation in the field of fluid mechanics. So here on the x-axis, we have the Reynolds number, so don't worry about that. So this is a parameter that tells us how large the system is and how fast the fluid actually moves. For example, if we have a small bug in the slow breeze, we have a low Reynolds number. If we have a very large wind farm, we have a very large Reynolds number, and this is the log scale. And here on the vertical axis, we have the computational cost, or the number of grid points that we need to solve this kind of problem. And the blue line here shows the computational cost to solve any of these problems. I also plot this red line here, which shows the largest simulation today, that only a few places in the world actually have access to that. And this green box here is the feasible practical simulation that we can use, for example, at the universities and also at the industry. So as you can see here, even if we go now to the largest supercomputers in the world, we can only solve some of these problems, maybe the small scales. And many of these problems that we are really interested in, we cannot even approach currently. So this is a long-standing problem in fluid mechanics and turbulence. And that actually left all the engineers and scientists with only one viable option, which is the turbulence modeling. So somehow we want to use turbulence model to reduce the computational complexity, and then we can solve this kind of problem. So, and today I'm going to talk about one of these models, which is the most promising one, and the state of the art in this approach, in this basically field, which is called large eddy simulation. So if I show you this, basically now this black line here shows the computational cost that we need to solve this problem with this approach. And as you can see, now we are able basically to solve this problem with large eddy simulation. But what is the main concept behind that? So as I said before, large eddy simulation, or LES, is the state-of-the-art numerical technique to solve this kind of complex turbulent flows. And the main idea, the main concept behind that is, instead of having very, very fine resolution or very fine grid to capture all those vertical structures that I show you from the Da Vinci's sketch, so we are going to use, perhaps in this case, larger grid, and we are only solve or simulate large structures, large eddy, and we model only the small scales, everything below this computational grids. So by using that, we can reduce the computational cost, and now we can solve this kind of problems. But the main challenge, as I think you can guess, then the accuracy of this approach would depend on the accuracy of this kind of model that we use. So if we can have a good and fast and accurate model, so we can use this approach with more confidence. So we can design systems that we can confident about our design. So, and this problem becomes even more critical, more challenging when we go through basically in the region very close to the surface. Why this part is very important? Because all the interaction between the fluid and the solid surface, if we have, happens in a very thin layer close to the surface. For example, air around the wing of the aircraft, or the air around the blade of the turbine, or the fluid or water close to the impeller of a pump. So everything happens there. And we use most of the major part of our computing power only for that layer. So the idea here in this project, can we come up with a fast and accurate model for that? Because if we can do that, we can solve this challenge, this issue, and then we can use numerical simulation in more confidence in this field. Just to show you what actually this near-wall dynamics or near-wall turbulence that I'm talking about look like, I really like this picture from Lake Geneva. that is a very, very rare natural event, that we can see the footprint of these long or elongated coherent structures near the surface. So these, I think perhaps you can see this, it highlighted with white, this elongated meandering structure there. They are completely unsteady, they are high, kind of multi-scale, they are nonlinear, they are very complex to be modeled. And here, I show you another kind of picture. This comes from the high-fidelity numerical simulation. They are completely different scales, but you can see the similar pattern here. So as I said, the idea here is, can we come up with a model, with an accurate model to predict and solve these complex systems? But before that, I want to say that what is the current status and what I'm proposing in this project. So, as I said before, turbulence is highly unsteady, is nonlinear, is multi-scale, high-dimensional, is very complex. And as you can see, if you want to model that, the current approach mostly based on some simplified assumptions. Basically, researchers try to simplify this problem with many, many kind of, approximation. For example, ignoring the unsteadiness, ignoring the nonlinearity, to come up with a simple model that can have some sort of prediction. And most of these models also develop for very kind of specific and idealized condition. And that's why they typically fail when we have complex systems. For example, when we have systems associated with transition or unsteadiness or acceleration, or when we have buoyancy, when we have the effect of heat transfer in the fluid part. So I'm not going to go through the detail of all this physics-based model. I'm going to, which are most, still is a kind of is a hot topic, is an active research in fluid mechanics, but all of them are based on incremental improvement in the existing model. What I'm proposing in this project essentially is a different approach, is a kind of paradigm shift from purely physics-based model to something that we call physics-constrained data-driven model. So these days, we have huge amount of data. We have vast and increasing amount of data in fluid mechanics and turbulence from simulations, from experiment. In parallel to that, we have the domain, we have the area of data science, that we have very sophisticated, very advanced machine learning models. So the idea here is, can we come up with a model, and this is what we are going to do, to build a specific machine learning model that can capture the data, that can basically follow the data, which is the reality. So we want to minimize those kind of assumptions that I said before, but also to acknowledge kind of the physics of turbulence, which is, as I showed you before, is a very old kind of problem in physics. So we know a lot about that. So we want to use this kind of novel tools, which is coming from the data science and machine learning domain, and we want to apply that to this field to come up with a better and more accurate models. So the reason actually I call it physics constraint is because this is different from the typical machine learning tools, for example, used for Amazon or Netflix, that they have huge number of users with large number of choices, and they can tell you what you are going to watch next. But in this case, we have a problem which is highly sensitive because we are using that for transport, we are using that for energy. And everything there should be follow the physics at the same time, but also should be reliable. So my hypothesis here is an approach like this is going to basically closely capture the nature of turbulence in these complex systems and can give us kind of level of accuracy comparable to the exact solution, but with much, much lower computational cost. So what is the outcome of this project? So as I said before, we want to simplify it. We want to make this kind of fluid mechanics as a tool or numerical simulation as an approach that everyone can use that. Somehow it comes through the democratizing the numerical simulations. So for academic means that we can now solve numeric or fluid mechanics problem that currently are out of reach. So those kind of large systems that I showed you before. And this project, together with a side project that we have on the data-driven fluid mechanics for industry, means that we can enable fast-paced engineering design and decision-making. So a little bit about the practicality. So for this project, Beside myself, I have one postdoc and a brilliant, super smart PhD student that we are working on this project. And also, I have academic collaborators from Penn State, from Stanford, from DTU, and also from Digit Center at Aarhus. They are among top researchers in the field of fluid mechanics, turbulence, aerodynamics, machine learning. So we have a great team that hopefully we are going to tackle one of the hardest problems in computational science. So at the end, I want to thank especially DFF for supporting my research. This is a timely research in engineering and in particular in fluid mechanics, and I'm really happy that it's supported by DFF. And also, I would like to thank my former and current master student, PhDs, and postdoc on this, and also my other collaborators that we work together on different projects related to fluid mechanics. Beside the ones that I showed you before, I want also to thank some of my collaborators from Hopkins, from Durham, from my great colleagues from AU, and also industrial collaborators like Orstel, Grundfos, Kamstrup, and Siemens Gamesa. So this project is gonna kind of, together we are going to solve and one of the key challenge in the application of numerical simulations for fluid mechanics. Thank you.